In this example problem, we have an airboat in the Everglades accelerating across smooth water. They tell you a mass, they tell you a distance it covers, they tell you a time, right? So we've got a lot of stuff going on here, and they're looking for the acceleration of the airboat, and they want to know what is the force of that fan motor acting on the boat. All right, so like any problem, there's a lot of pieces to it, but let's start with drawing a little picture here. So I'm going to draw my fan boat here. Again, the picture is not that important here, but there's the hull of the boat. Let's draw a little fan, right? And this fan boat is starting here. There's our water, and it's going to finish somewhere in this range, right? And we know that this is a distance of 100 meters from here to here. We know that it takes a time of 7 seconds to travel that distance. When we get to the end, this fan boat is going to now be located over here, and it's going to have some amount of velocity, right? So it went from having no velocity, zero velocity, it's at rest at the beginning, to now having some unknown velocity. They also tell you the mass of the fan car. The mass is 1,200 kilograms. And if it's going from zero to some velocity, we also know that it is accelerating. So we know that we should have some acceleration to the right. All right, so we got a lot of pieces here. When we're dealing with time and displacement and distance, we should be thinking kinematics, right? And we have two kinematic equations, and the one that we're going to look at right now describes where we're located as a function of our acceleration, our time, how fast we're starting in time, and where we start from, right? And if we decide to call our initial position 0, then where we finish would be 100 meters, right? So that's our first kinematic equation. We can also look at our final velocity is AT plus v initial. If they cared how fast the boat was going at the end, that would be the equation we can use. Right? What we want to know, though, is A. We want the acceleration. So when we set up a kinematics equation, we can set up our ATVX table. Right? Just a way to organize all the variables that are in those two kinematic equations. And the things we don't know, well, we don't know our acceleration. In fact, if I find that, I have my answer to part A, the acceleration of the fan boat. They tell you that it takes 7 seconds to travel from rest, so v initial is 0, to some final velocity. They don't tell you how fast the boat's going at the end. And if it travels 100 meters, well, if we start at 0 meters, then it would be located at a position of 100 meters at the end. All right, so when we look at all this stuff and we look at our equations, again, a good strategy now is to put a little dot over everything you have. I have x final, I have t, I have v initial, t, x initial. The only thing I don't know is a. In this equation, I don't know v final or a, so I can't do anything with that yet. But lo and behold, I can use this first equation and I can solve for a in that equation. So I'm going to take that equation and I'm going to substitute the things I have. And that gives me 100 meters. Let's check our units first. I have seconds, I have meters per second, meters and meters. Since everything is in meters and seconds, and there's no mixed units, I don't have kilometers in there or hours or minutes, then I don't have to worry about the units. I'm going to get an answer for an acceleration in meters per second squared, and velocity would be meters per second, as long as I plug in those numbers as they are. So I'm going to go back to my equation here. I got 1/2. A is unknown, and we have our time of 7 seconds, and that is squared. My initial velocity is 0, and I multiply that times 7. Well, 0 times anything is 0, and I'm starting at 0, so that goes away. So my equation simplifies now. I can clean some things up right now. I can multiply some stuff. Again, the algebra steps here. You can decide to do what you want to do. Let's just clean up the right side. 100. 7 squared is 49, so I have 1/2 times a times 49. I can clean that up a little bit further. Get 100 is equal, well, 1/2 of 49 would be what? 24.5? 24.5 times a. All right, 24.5 times 2 would give you 49, so that appears to work. And now let's solve for a. If I divide by 24.5 on both sides, that isolates a. I now have 1a. I'll pull out my calculator now. We can confirm too that 1/2 of 49 is indeed 24.5, right? And now I'm going to take 100 and I'm going to divide by that answer in my calculator. And I get 4.08. So I get an acceleration of this fan boat of 4.08 meters per second squared. So what does that mean? Well, every second I'm gaining 4 plus meters per second, which means after about 7 seconds, I would be going about 28 meters per second. Again, I could plug this in if I wanted to know how fast the boat's going. Well, now I have A, and all I need to do is multiply it by the times 7, and I would have my final velocity. But it's not asking for that. All it's asking for is the acceleration for part A. Well, what about part B? Well, they tell us about this boat. They want to know, what is the force of the fan acting on the boat? Well, we have a fan boat. It has mass. It's accelerating. And I hope you're thinking, boy, Newton's second law, right? Newton's second law suggests that the net force, F net, the total amount of force that is unbalanced acting on that boat would cause the boat's mass to accelerate, right? And when I look at trying to find the net force, it helps to draw a free body diagram. So I'm going to draw a free body diagram of this boat. It's a good habit anytime you're dealing with forces. And so let's draw the boat again. Again, I'm not a great artist here, but I'll draw the hull of the boat. I'll draw the fan. All right. And let's draw all the forces on it. Well, we can draw a little dotted line to indicate the surface of the water. We always have gravity. That would be the force due to gravity. But this thing's accelerating to the right. Again, not on a free body diagram, just off to the side. We know that we have an acceleration this way, which would indicate that our net force would also be to the right. So these up and down forces, Fg, this thing should not be falling. Well, why doesn't it fall? Well, we have water applying a normal force or a buoyancy force to cancel Fg. So those forces actually aren't really a factor in this problem. All we care about are the forces that act to move the boat to the right. And what is that force? Well, Newton's third law says that if this fan pushes air to the left, well, then the air would actually be what is propelling the boat to the right. You might consider this air as the force from the fan. That is really how it propels us up. But this is really a third law interaction. Now, there's other air action here. There's air resistance, which would actually act to the left. There's some friction with the water. But when they say negligible, that just means we can ignore those two forces. So we're going to ignore friction and resistance. So this thing is now being pushed to the right only by this fan force. So the net force, F net, is equal to M times A. But F net is really the force of that fan motor, right? The fan motor is what is causing that unbalance of force. And that is causing the mass of this boat, which we know is 1,200 kilograms, to accelerate. And we found that acceleration. It's 4.08 meters per second squared. And so we can now calculate and find that our answer, if I take 4.08 and multiply it times the mass of that boat, we know that, boy, there's a pretty large force. 4,898. 4,898. The units are kilograms times meters per second squared, and that is what we call a Newton. So this is the force of our fan motor that is causing that boat to accelerate along the water. So hopefully this makes some sense as we walk through this problem. It's a combination problem. We have kinematics in this first part for part A, and in the second part, we're looking at dynamics, which is looking at these forces and how they cause objects to accelerate. We have an unbalanced force, the force of the fan motor, which is really a third law interaction that propels that boat, accelerates it at a rate of 4 meters per second squared.